So I hope all of you are doing well. My name is Shriya Bansal and I'm currently working as a software engineer at Microsoft. And now in this video, we are going to talk about our fourth scheduling algorithm, which will be based on round robin scheduling. So far, we've already covered a first come first serve scheduling. We've then covered about shortest job first scheduling. And after that, we also did take a look at priority scheduling. In this video, we are going to take a look at round robin scheduling. So first, let's take up the definition of this algorithm first, and then we'll go ahead and take multiple examples. So round robin is actually the oldest and the simplest scheduling algorithm. The name of this algorithm actually comes from the round robin principle, where each person gets an equal share of something in circle or in turns. It is mostly used for scheduling algorithms in multitasking. This algorithm method helps for starvation-free execution of processes. Okay, so now let's deep dive a little bit more into this idea and then talk about the concept of round robin scheduling. I'll first take up a few important points that you need to know, and then we'll take relevant examples as well in order to understand this concept in detail. Okay, so the idea is always remember that first of all, round robin is a preemptive scheduling algorithm. Okay, that means if another process is there, the current process will be stopped based on the priority that we have thought of. Secondly, what happens is the processor does not fully execute a process. The processor basically gives a certain period of time to each and every process in cycle. So let's say if there is a process P1, P2, P3. So first it will, let's say, give 3 seconds to this, 3 milliseconds, let's say, to this process. Then wherever this process has many executions left, it will stop and directly go to this and then directly go to this. And then it will come back and give 3 milliseconds to all of them. And this kind of a thing will keep on happening until and unless all the processes are not fully executed. Okay. So what happens is in round robin, each, I would say, process is provided a fixed time to execute. Okay, each process is allocated a fixed time to execute, and that fixed time is basically known as a quantum. Okay, and then what we basically say is once a process is executed, right, for the given quantum or the given time period, right, it is preempted, it is stopped in between no matter how much of it is left. It is preemptive and other process is executed for the given time period. Okay, and here, because of this, since we are switching from one process to another process, so if you're switching in between, you need to save the context of the old process and load the saved context of the new process. Okay, so here we basically use the concept of context switching to basically save the state of preempted process, and this is valid for any preemptive scheduling algorithm. Okay, that is what the overall idea is behind the concept of round robin scheduling. Okay, so what we can do is now we can take an example as well to fully understand this concept in detail. I think there is an example given here as well, wherein you can see that process is basically P1, P2, P3, and the burst time is 24, 3 and 3. Okay, so what is happening is here the quantum time is taken as 3 unit. Okay, so first the process P1 is basically executing, right, and the rest of the processes are executing after it. And I think here the quantum is 4. Let's take the example over here only. So if I have P1, P2 and P3, if this is the process, the burst time is 15. What was the burst time? 24. 3 and 3. And the quantum is 4. So what will happen is, first we will have the P1 process which will execute from 0 to 4, and then it will simply be preempted and the logic will be given to P2 process. Now here the quantum given is 4, but the entire burst time of the process is 3. So it will stop after 3. And then it will be given to this process, which is P3 again. The quantum is 4, but it will execute in 3 seconds. And then it will come back to this. And then it will execute for 4 seconds again. And then none of these processes are left. So this is the one which is getting again the processes. Okay, and this is how this is basically working. So you are allocating the resources in a cyclic format over here. Okay, you want to take another example, we can take that as well to understand this concept in detail. Okay, so we have the process, we have the burst time, and let's say in this example we take the arrival time as 0 for all. So we have P1, P2, P3 and P4. The burst time will be 21, 3, 6 and 2, and the arrival is same for all of them. So how would this process occur? First you have to decide the quantum also. Deciding the quantum is also a task. You don't want to take a very small quantum also, because then a lot of time will be taken up in context switching, and you don't want to take a very large quantum as well. Let's say here the quantum value is, let's say 3 over here. Okay. So in that case, what will happen over here is, or let's say we take the quantum to be 5. So first the P1 process will be there. It will execute from 0 to 5. Then we go to the P2 process. Okay. It only has 3 units. So it will take not the entire quantum, but just a part of the quantum, and this is completed. And then we have the P3 process. P3 process has a burst time of 6. So it will execute till 13, and it still has 1 quantum left. This still has 16, execution left over here. For P4, it will only take 2. So this is ending at 15 for P4. Okay. And with this, P4 is also ended. Now we go back to P1 again. P1 basically gets over here 5, which is 20 over here. Okay. And now this is left to 11. Now P2 is already completed. So we give to P3 only the left processes. This is P3 and this is 21. Now this is also executed, and this one will keep on getting repeatedly. So here it has 12 left. So P1 will basically execute till 32. Clear to everyone how this basis of round robin scheduling is basically working, right? And how exactly we are able to schedule the processes. Like you can see, this is basically I would say preemptive kind of a procedure, because we are stopping a process in between and then calculating it. So using this, now what you can also do is, if you have to calculate the average waiting time, first you calculate the turnaround time. Okay, turnaround first. Before that, you have to mention the completion time. Completion time for P1 is 32. The completion time for P2 is 8. The completion time for P3 is 21. The completion time for P4 is 15. Turnaround time is basically completion time minus arrival time. Arrival time is 0. So completion time will be equal to this only. And then we have the waiting time. Waiting time is turnaround time minus the burst time. So 32 minus 21, which will be 11 over here. Then we have 8 minus 3, 5, 21 minus 6, 15, and this is 13. Okay. So what will be the average waiting time? 11 plus 5 plus 15 plus 13. So if you calculate this, 11 plus 5 plus 15 plus 13, which is 44 by 4, which is 11. So 11 milliseconds is the waiting time on average over here for this process. Okay, and that's what the overall idea is about this particular process. Okay, you can take an example now here as well. That's why I'm taking more and more examples, because the more examples you take, the better you learn. So let's say there is a process P1, P2, P3, P4, P5 and P6, and now the arrival time is not same. So this is 0, 1, 2, 3, 4 and 5. Okay, and then we have the burst time. Burst time is 5, 6, 3, 1, 5 and 4. Okay, so this is what it is over here. Now let's take a look at how the execution will happen. This is the Gantt chart. Here we are at t is equal to 0. At t is equal to 0, there is only one process, okay? And this is the only one which will execute as well. Let's say the quantum is basically 4. So it will execute for 4 units, 0 to 4. And it still has one execution left, okay? Now what happens is, by the time we come at t is equal to 4, we have all these processes now. Okay, now what will happen is, out of all of these processes, right, what will you do is you will follow a round robin technology. So the next one is P2, okay, which will basically have the allocation for 4 units. So this is P2 over here. So this is P1, sorry. This is P2, which will again get it for 4 units. And this is basically left with 2. Now after this, we will give it to P3. Okay, now with P3, it will only execute for 3 units because its burst time is 3. So this is left with 0 and this is done as well. Now we go to P4. P4 has a burst time was 1 only. So we have P4 and it's done. Okay, then we have P5. P5, it will run for 4 units and it will still have 1 execution left. Now this is also done. Now we have P6. P6 will basically execute till 20 and now this is also done. Okay, now you will go back to the leftover processes. This was also done. After this, you go back to P1. P1 still has 1 left. So you execute P1. Then you go to P2. P2 still has 2 left. So you do for P2. Okay, and then you go to P5, which still has 1 left, and this ends over here. Okay, so this is how you basically calculate for a difference of arrival time. It won't make a lot of difference because by the time you come for the next arrival, you're still going to move in the sequence. Okay, with this, what we do now is, first we calculate the completion time. The completion time for P1 is 21. For completion time for P2 is 23. The completion time for P3 is 11. The completion time for P4 is 12. For P5 it's 24. And for P6 it's 20. Okay, that is what the completion time basically is. Let's see for P5. We have 5 processes or 6 processes. So we have 4, 8, 12. And if we look at the arrival time also, I'm just confirming one thing, that when we had for P4, then we had for P5 as well over here, right? For P5 we had, and then somehow this is correct, and then we have the turnaround time, which is completion time minus arrival time. So this is 21, 22, 9, 20, 50. And then we basically with this have the waiting time. The waiting time is turnaround time minus the burst time. So 16, so 16, so 6, 8, 15, 11. So when you add up all this, it is 16 plus 16 plus 6 plus 8 plus 15 plus 11, which is 72 over here. So the average waiting time over here is 72 by 6 equal to 12 milliseconds. Okay, so this would be your average waiting time over here. Okay, so we've taken both the examples. We've taken an example where the burst time, arrival time is same, and we've also taken an example where the arrival time is different. And you've seen in both cases how does it work. Okay, that's what I'm trying to help you to understand as well. The more examples you take, the more easier it will be for you to understand the topic as well. Okay, the theoretical part is quite easy. It doesn't involve a lot of logic, and it's quite easier to work with these algorithms. Are you actually able to go ahead and implement the logic or not? Okay, so that's what it is. In round robin scheduling, every process gets a perfect scheduling, or I would say a quantum of time, and it keeps on getting that quantum of time in rotation. Okay, and whenever a process is completed, it basically goes out of that. Okay, some of the disadvantages of using the quantum scheduling over your round robin scheduling is that higher the value of quantum, the higher the response time will be, because here the quantum value is very high. So you're actually giving a big chunk of resources. So the CPU is occupied for a very long period of time continuously. Okay, but if you will keep the quantum time as very low, there will be a lot of context switching over here. Okay, so that is why deciding the perfect quantum time is very, very difficult. Okay, I'll write it here as well, that the lower, or I would say the higher the quantum time, higher is the response time. Lower the quantum time, more is the context switching overhead, because your quantum time is so low that you're just spending a lot of time in switching the context itself. And the last one is deciding the perfect, hence deciding the perfect quantum time is very difficult. Okay, so that's what the overall idea is over here. But round robin is actually one of the successful ways of doing that, because it does not lead to starvation at all. In priority scheduling, we could see that there can be situations where it can lead to starvation of a process, whereas when you're using round robin, you can actually guarantee that there is no situation of starvation or the convoy effect as well. Okay, that is also something cannot happen. So if I have to list a few advantages, we can say there is no convoy effect. Okay, and along with that, there is no concept of starvation also that can happen using this. Okay, and along with that, there is fair allocation of CPU as well among all the resources, which has been pretty much our goal from the start. Okay, so with this, I hope the concept of round robin is clear to everyone, and you have understood with a lot of examples how the idea of round robin works. Okay, so thank you so much for taking a look at this video, and I will definitely meet you in the next one. Bye.